Welcome back to Physics Land, everybody. Let's talk about conservation of energy. Prior to this, we just got finished talking about the work-energy theorem, and really this is not going to be much different. A lot of what we're going to talk about with conservation of energy is very similar in a lot of ways. Let's go ahead and start off the bat. One way that it's similar is we're still going to draw pictures, okay? And pictures are very simple for us. Arrows going up, arrows going down, arrows going left and right. Somebody going down a hill could be something like this. Pictures very similar like that. And in those pictures, we also need to label EI, which stands for initial energy, and EF, which stands for final energy. Those two, with the work-energy theorem, the reason we needed to know EI and EF is because we had to decide what type of energy was present in the system, according to the problem we were reading, at those two locations, or whatever was going on in the picture. And for work-energy theorem, the choices we had were either potential energy, or kinetic energy, or zero. Because with work-energy theorem, we also had problems that were things like starting from rest and coming to a stop. In those cases, energy is zero, at least mechanical energy is zero. And also, if something's sitting on the ground, energy was zero because it had neither height nor kinetic energy. So remember, potential energy is based on height. If an object has height, it has gravitational potential energy. That's what we were talking about. And if it's got speed, it's got kinetic energy. Don't forget about that. With conservation of energy, we're actually going to add another form of energy and take one away. And the fourth one that we're going to add, people often say, is it chemical energy? Is it heat energy? No, it's actually both. It's both potential energy and kinetic energy. In other words, at the same time, if an object at the same time has height and speed, then it's got both potential and kinetic energy. And then people are thinking, wow, we got 4 kinds of energy instead of 3. No, we don't actually have 4. We're getting rid of this one. With conservation of energy, there is no zero. And the reason is because the law of conservation of energy, we've actually already talked about. The second bullet point, most people can complete. Energy cannot be created or destroyed. Most people know that. People coming into my class can complete that sentence. But the ramifications of that are really important. The ramification is that in a closed system, is similar to a closed room. A room that's closed means nobody can get in and nobody can get out as long as the room is closed. And it's the same with energy. The biggest thing you need to know about a closed system for us is a closed system really just means no friction. That's what we're basically dealing with here. If there's friction involved, then energy can escape in the form of heat. So we're not going to be dealing with friction with this stuff. In a closed system, if that's the case, and energy can't be created or destroyed, that means the total amount has to remain the same. It has to remain constant. And this right here is a really, really important point. Really important point. The total amount of energy has to remain the same. Very similar to in your bank account, you might have money change hands from your savings to your checking account one way or another. If you put money from your savings to your checking or from your checking to your savings account, vice versa, money is changing accounts, but you haven't gained or lost any money. That's the point of the law of conservation of energy. And we've actually already talked about that. And that's the reason why energy cannot be zero with conservation of energy, because that means if it was zero at any one of these points, that means it must be zero at the end, which means nothing happened in between and we can't analyze anything that goes on. So we're not going to be using zero with the law of conservation of energy. It's either potential, kinetic, or both. As I said before, a closed system is no friction, which means that no energy is lost as heat. Sometimes energy is lost as heat. We talked about that with the work-energy theorem, where work equals change in energy. That's not going to be the case here with a closed system in the law of conservation of energy. In reality, closed systems don't exist very often, but it's useful to understand the principle of the law of conservation of energy by talking about closed systems, not to say that this happens all the time, but to understand how this changes and the fact that as a whole, the universe is theoretically a closed system. And you can also to some extent think about the Earth as a closed system. But if we understand the baseline of what happens in a closed system, then we can begin to analyze differences that happen in systems that are open. Right now, we're only considering kinetic and gravitational potential energy. Therefore, at any one time, the total energy has to be equal to the potential energy in a system and the kinetic energy in a system. For instance, in a previous problem, I think when we were talking about work energy theorem, I took a bowling ball and I lifted it up. All right. Now let's imagine it's up in the air and I'm going to drop it. Okay. Things that are dropping is one example of conservation of energy stuff. As a matter of fact, if you want to turn your notes on the side, if you were here, you should have written this. COE means conservation of energy. I'm going to tell you the 3 types of problems that we're going to have with conservation of energy. The problems will be about roller coasters. We all know what a roller coaster is. It'll be about a pendulum. Pendulum is anything that's swinging back and forth, right? Or anything that is rising or falling. Notice I didn't put lifting in that list, and there's a reason why. Roller coasters, pendulums, rising and falling. The reason why lifting isn't in there is because technically lifting something is not a closed system. Energy is constantly flowing into that object. When I was lifting the bowling ball, energy was flowing from my muscles into the bowling ball in the form of potential energy. So its energy was not staying constant. But once I let it go, assuming we don't have any friction, which we're not going to deal with, we're not going to consider at least in conservation of energy, once I let it go, now I have a closed system. There's no friction. I'm not giving the ball any more energy, and gravity is simply pulling it down. So this is an example of a picture we would draw. Initial energy at the top, final energy at the bottom, simply because this one happens first, this one happens second. And we're always going to ask ourselves, what kind of energy is going on? Well, at the top, we have height, and there's no speed yet because I haven't dropped the ball, and so it's potential energy. At the bottom, this is right before the ball hits the ground, the instant before it hits the ground. It's either potential or kinetic or both. It has all speed right here, lots of speed. It goes faster and faster on the way down, but it's lost its height. It doesn't have any more height yet. So there is no potential energy. No potential. It's all kinetic. So potential energy has been converted to kinetic energy. If we draw a graph of this situation, energy versus time, let's say, time / it doesn't really matter for us. The graph looks slightly differently depending on what you put on the x-axis, but it doesn't matter for us. There's 3 lines that we're going to draw. We're going to draw many of these graphs in these notes. The first line is total energy. We read that total energy stays the same. Okay, so that means that at the top, let's say there was 200 joules of energy up here. Well, if the energy stays the same, all of this energy got converted to kinetic energy. That means I have to have 200 joules of kinetic energy at the bottom, which means that my total energy is 200. And let's go ahead and put 0 at the bottom because that makes sense. Total energy stays the same, and the total energy is 200 joules. So my total energy line is going to be right up here at the top, E subscript T for total energy. That's always that way. The line for total energy will always be straight across, always at the top. That is the concept of the law of conservation of energy because the total energy stays the same. The next line is going to be for potential energy. What happens to the potential energy of this ball as it drops? Well, the height of the ball will decrease as we go down. Since the height is decreasing, so will the potential energy. So the line for potential energy will look like this. Potential energy decreases. Kinetic energy. What happens to kinetic energy as the ball falls? The ball's getting faster and faster and faster, so kinetic energy must increase. And realistically, this line would be curved depending on which of these you use, but we're just going to go straight for right now for something that's rising and falling. Kinetic energy would increase, and I want you to notice what happens. As the potential energy drops, the kinetic energy rises. As kinetic rises, potential energy drops. That always has to be true with conservation of energy because at any time, the total energy has to be the equivalent of whatever potential is plus whatever kinetic is. And the total stays the same. This total amount has to stay the same. So if potential energy goes down, kinetic energy has to go up to take its place. And the cool thing about these graphs is if I draw a vertical line at any place on this graph, whatever that amount is, added to whatever that amount is, has to add up to whatever the total is, 200. For instance, if I have 50 joules of kinetic energy here, I know that I have to have 150 joules of potential energy here because both of these have to add to 200. The total always stays the same. No matter where I draw that vertical line, these two amounts have to add to 200. And the part where they cross is very interesting because we know they both have the same amount at that point. And if they both have the same amount, the only number that is the same that adds to 200, they both have 100 joules right there, right in the middle. So this is how graphs look for the law of conservation of energy. Total energy always stays the same. It's a straight line across the top. Potential energy, notice, follows the height. Potential energy follows the height. We said this before. Height decreases, potential energy decreases. Kinetic energy will always be the mirror image of potential energy. It has to do the exact opposite because they always have to add to the total. So that means now you know actually two ways to find the kinetic and potential energy an object has. The first way is you can use the equations that I've given you. And that's for kinetic energy, we had mv squared over 2. For potential energy, mgh. Those equations will give you the amount of potential and kinetic energy. And that's great unless you don't know some of these key things like mass or speed or height. If you don't know those things, there's actually another way, and that is to subtract from total energy. Subtract from ET, not extraterrestrial, but total energy. And that's what we did right here. I knew if I figure out that this is 50 joules, even if I don't know the height of this object right here, I know the potential energy has to be 150 because they have to add up to the total. That is the power of understanding conservation of energy. And actually, I wrote this in the wrong place. All of these problems right here along the side, you can actually write those right in here. Those are the three types of problems that we're going to have for the law of conservation of energy. So that's the basic concept of this law of conservation of energy. And you need to understand these concepts. In the next video, we'll talk about how to do some of the math behind the concepts.